In this video, I'd like to talk about the math question of the day for Sunday, May 28th, 2023. And with this problem, we're given a sequence here, a sub n, and we are asked to find this limit as n approaches infinity of the absolute value of this ratio of the n plus 1 term in our sequence divided by the nth term. And this is just known as the ratio test. And we can use this to determine what this sum is, this infinite sum of each of the terms of this sequence, and whether or not it converges or diverges. And questions like this are typically seen in a Calculus 2 class. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through it. And before we look at the specifics of this problem, let me paste in a definition for this ratio test. And for that, we'll actually need just a bit more room. But let me quickly paste that in. And essentially what this is saying is that if we have some series, then if we look at this limit, which we call L, where we compare the ratio as n goes to infinity of the n plus 1 term divided by the nth term. And if this limit, L, is less than 1, then we can conclude that the series is absolutely convergent. If L is greater than 1, then the series is divergent. However, if L is equal to 1, we basically don't know anything about the series. Or, in other words, we don't know if it's divergent, convergent, conditionally convergent, or absolutely convergent. So, to apply this ratio test, we need to look at the nth term, which we have right here, and the n plus 1 term. So let's first find that n plus 1 term. We have a of n plus 1. Anywhere we see n in this sequence here, we will plug in n plus 1. So we have n plus 1, since we have n out front, multiplied by 5 over 4 raised to the 2 times by n, or now we have n plus 1, and then we will add 1 to that. So let's simplify. We have n plus 1 multiplied by 5/4 raised to the 2n plus 2 plus 1. So 2n plus 2 plus 1 would just be plus 3. And from here, we can look at this limit, since now we know the n plus 1 term and the nth term. And that will tell us whether or not this series here, this infinite sum, will converge or diverge. So let's now consider L. This is the limit as n goes to infinity of the absolute value of this ratio. And we have the n plus 1 term up top. So let's write that in. We have n plus 1 multiplied by 5 over 4 raised to the 2n plus 3 power. And all of this is divided by the nth term, which is n over, multiplied by 5 over 4 to the 2n plus 1 power. So let me make a little bit of space, and we can keep working on this. And I'll start by just rewriting this a little bit clearer. Now, within this limit, this ratio here inside the absolute value, we can make a few simplifications. So we have this 5/4 raised to the 2n plus 3 in the numerator and 5/4 to the 2n plus 1 in the denominator. So let's rewrite that using exponent properties. And I will just work on that off to the side here. This 5 over 4 is raised to the 2n power, but we can multiply this by 5 over 4 to the 3rd power. With exponent properties, we can just add the exponents since we have the same base. And we're dividing by 5 over 4 to the 2n power multiplied by 5 over 4 to the 1st power. And we have this same factor in the numerator and denominator, this 5/4 to the 2n power, which we can then cancel out. And we have 5/4 to the third divided by 5/4 to the first. We can use exponent properties since they have the same base. We can subtract the exponents so that we get 5/4 raised to the second power. So with that simplification, we can rewrite our limit. We still have the limit as n goes to infinity of this absolute value of this expression. We have n plus 1 divided by n. And in our numerator, we still have this 5/4, but now it's raised to the second power. And 5/4 to the second power, we can simplify that. We can actually square that. That will just be 25/16. So let's write that in. We have 25/16. And because this does not contain n in it, we can actually factor that out so that it's on the outside of our limit here. So let's rewrite this down here. We have the limit as n goes to infinity, and actually, like I mentioned, let's factor that out. We have 25/16 multiplied by the limit as n goes to infinity of the absolute value of n plus 1 over n. And with this rational expression here, we're letting n go to infinity. There are a couple ways to think about it, but essentially, as n gets bigger and bigger, we are mainly concerned with the highest power of n, which in this case is just a linear term in each of these, n to the first power, and we'll compare their coefficients. Since the bigger that n gets, the less important this constant added to n actually becomes. For instance, if you plug in, let's say, a billion plus 1 is still basically a billion. And then we're going to divide by a billion. So as n goes to infinity, we look at the ratio of the coefficients here, of these highest power terms, and this limit will just be 1/1. Now, a more mathematical approach, rather than just thinking it through, is that we can multiply the top and the bottom by 1/n. And when we do that, let me again make bit more room here. We can now simplify this so that we get 25/16 multiplied by the limit as n goes to infinity of this absolute value. We distribute the 1/n so that we get 1 there, and 1 times 1/n is 1/n, divided by n times by 1/n, which is just 1. And now we let n go towards infinity, and for this expression here, the denominator just gets bigger and bigger while the numerator is fixed at 1. So this right here will approach 0. And you can see we just get 1/1. So that our limit is simply 25/16. And since our L value is bigger than 1, if we go back up to our definition of our ratio test, we can see that when L is bigger than 1, this sum here, this infinite sum, is divergent. So we find our limit, L, that's 25/16, and then to answer our second question, based on our answer from 1, what does the ratio test say about this infinite sum? We now know that this sum would be divergent. It does not converge to some real number.